Our project is called Compare and Compress, a compression comparison. We implemented several different lossless compression algorithms and analyzed them for runtime as well as compression efficiency.
Our first compression method is run-length compression. Run-length compression takes a string and transforms it into an encoded form by walking through the string character by character and counting consecutive like characters. When consecutive characters are no longer the same, the count is reset for the next unique character. To decompress the string representing characters and counts, we reverse the string serialization and then concatenate characters together, concatenating a character the number of times its count dictates. Run-length compression runs quickly but has the potential to be an ineffective compression method if the string in question does not contain large spans of consecutive like characters.
Our next algorithm is Huffman coding. Huffman coding exploits the fact that each ASCII character is represented by exactly 8 bits, so it chooses to represent the more frequent symbols with shorter length codes and the less frequent characters with longer codes. To decompress, it replaces all of the codes with the characters that they correspond to. Since the codes are made such that no code is a prefix of another code, the decompression is unambiguous. Huffman coding runs in linear time, but it's most efficient and most effective for files with low entropy, essentially files that are written in English. Other kinds of files like PDFs or images are much less effective to compress.
Our next algorithm, Lempel-Ziv-Welch, constructs a dictionary relating strings to codes. It translates recurring patterns of characters in the input string into integer codes that it records in a dictionary. To decompress, it uses the dictionary it built up during compression to retranslate these codes into plain text. This algorithm is efficient for strings with repeating characters and sequences of characters that recur several times in the text, and it runs in linear time.
The Burrows-Wheeler transform is not actually a compression algorithm by itself. Rather, it takes a string and transforms it into a permutation of its characters. This permutation is chosen by grouping together letters with similar context. As a result, the transformed string will contain more consecutive runs, which make it more efficient for another algorithm, in this case run-length encoding, to compress the string. The original string can be recovered from the transformed string and the row index, which we store at the beginning of the new string. The runtime for the forward Burrows-Wheeler transformation is O of n squared times log n, because it requires a lexicographic string sort. The reverse Burrows-Wheeler transform is faster. It is most efficient for text files where the characters have similar context.
This is a table showing some of the results of our compressions. We can see that each of these compression algorithms is good for a particular type of file, so there is not always a clear-cut best algorithm. For example, here, run length is extraordinarily effective for files with lots of repeating characters, in this case the lyrics to the song 99 Bottles of Beer on a Wall. However, when run on a different kind of file, such as the American Constitution, Huffman coding clearly outperforms the other two compression algorithms, so there is no overall best algorithm.
The functions that we implemented work best for plain text files. Pictures and video files do not compress too well, since they have high levels of entropy.
Despite increasing space capacity, data compression nevertheless remains an important and interesting computer science problem.